for the first slide, I just wanted to show people sort of to first order why we care about meteorites in the first place, other than the fact that they're from space, so obviously who wouldn't want to study them for a living. But there are two primary reasons, or rather two different types of meteorites that give us information. So one type of meteorite, for example, meteorites that are solid iron metal, they tell us what planets were like in the early solar system. So many of our meteorites are actually bits of things like the Earth's core, except unlike the Earth, they didn't survive, they got broken up, and we get the pieces today. But there's a second type of meteorite, and these are broadly called chondrites, and they're of particular interest because they tell us what the solar system was like at the very earliest stages. So the meteorite I have there in the picture is called Allende. It fell in Mexico in 1969, and you can see there's sort of a black, almost cement, what we call matrix, and within that matrix are a lot of round spherules, which we call chondrules, a lot of weird shaped white things, gray things, and all sorts of other fascinating inclusions. But the reason why meteorites like Allende are important is because the sort of white or gray blobs tell us what we think the solar system was like at the very, very earliest stages. So right as the sun was forming, right as rocks started to form in the solar system. So that's sort of what, how we learn about the very earliest stages of how planets form. The chondrules, which are the circular sort of minerals like olivine and pyroxene that Andy was talking about in his spectra, we think those tell us about processes that are happening somewhere in the disk of gas and dust out of which planets form, but depending on who you ask, they mean different things and come from different places. And then finally, the matrix, which is the black material that makes up a lot of these rocks. We think it comes from farther out in the solar system, but we really don't know that much about it because it's very fine-grained, and when things, when planetesimals grow, like Vesta or Ceres, and get big, those really fine-grained materials are sort of the first things that end up being changed and altered. So if you want to go to the second slide, this just gives you an idea of the specific sort of asteroids, or meteorites rather, I'm interested in, and the ones that we might start thinking about when we go to Ceres. And like Andy was saying before, Ceres looks mostly black, and as you can tell from the three pictures there, those meteorites are also pretty much black, not too much there. And the differences between those types of meteorites are how much water we think melted and interacted, or how much ice melted and water interacted with the rocks as they were floating around in space. So not weathering when they land on Earth, not anything that happened yesterday or even 100 million years ago. All this stuff happened 4.5 billion years ago when the solar system was forming. And so that's my particular interest, is sort of thinking about what water and rocks are doing when planets are forming. So this slide here gives you sort of our metric for how we classify meteorites based on how much water's interacted with them. So at the far right, under green, you see Allende, and that sort of mineral inset there is a mineral called olivine, which again Andy mentioned, and olivine is pretty much what makes up most of the Earth's mantle and makes up a lot of other meteorites as well. And the second sort of meteorite in the middle there under the aqua or cyan is what we call a type 2 meteorite, and that meteorite is called Murchison, which landed in Australia in 1969. So between Allende landing, Murchison landing, and the Apollo missions to the moon, people had a pretty exciting year that year. But in that case, we actually can see minerals like the mineral on the inset there called serpentine, which you might also know as asbestos. And we know that forms when water and rock interact at lower temperatures. And then finally, at the very left there, under the dark blue, is what we call a type 1. And those meteorites are almost completely altered. We don't even see chondrules anymore. They're just balls of black clay. And again, you can see sort of the inset there for one of the minerals. It's pretty prominent. And that meteorite that's shown there, it's called Orgueil, and it fell in France in the 1800s. So even way back when, people were studying it and trying to understand what it meant and where it came from. And ironically enough, we still don't actually know. But that's pretty much the spectrum you have there, from things like Allende, which we think preserve all those different components from nearby the sun, at the very earliest stages of the solar system, up until what water and rocks are doing together on, bodies maybe like Ceres, and down through things that have been completely altered. So that's kind of where Andy and I tie in together. Is, for example, how we learned that we have meteorites from Vesta. People, like Andy, measured the spectrum in space, and people like me took meteorites in the lab and measured the spectra, and they're exactly the same. So can't quite do that with Ceres yet, but that's why it's really interesting to actually go there and get a better look.